Hi, this is Moser with Party Tricks for Chem Nerds. Okay, that's not really what this is. It's getting electron configuration with no counting whatsoever. We're basing it all on trends in the periodic table. How cool is that? When you have finished this video, you should be able to use the period in which an element occurs on the periodic table to determine the uppermost occupied main energy level. Okay. Know how to use the group in which an element occurs on the periodic table to figure out the subshells that are filled on the atom's uppermost occupied main energy level, and how to identify the blocks in the periodic table and use that information to predict the properties of the element based on its electron configuration. That's a lot. What you already need to know: how to write electron configuration in all three formats, and the difference between shells, subshells, and orbitals. Oh, and it'd be really handy to have one of these. So go get one of these if you don't already have one in front of you. Good. First of all, let's start off by defining periodicity. It's the tendency for something to recur at regular intervals. Like, we can say we go to school periodically. There's a periodic pattern to that. When we're talking about chemical elements on the periodic table, periodicity occurs in the atomic number and in chemical characteristics. This was part of the critical thing that was noticed by scientists who worked on the periodic table early. The other thing that we have to make absolutely certain we've got straight is our terminology. So when we're talking about energy level or shell, these are our main energy levels. These are 1, 2, 3, 4, 5, 6, 7, whatever. And our sub-levels or sub-shells are things like 3s. That would be all the s orbitals contained on the third main energy level. Or 4d, all of the d orbitals contained on the fourth main energy level. When we're talking about individual orbitals, we would talk about 1s or 2px, 3py. We could talk about the 3d5 orbital. Those are individual orbitals. So just make sure you understand the difference. Now, let's get back to that periodic table. We're going to start off talking about the periods here. And remember, the periods are the horizontal rows that go like this. So the first period, second period, third, fourth, fifth, sixth, and seventh. And those are all that we know of as 7 periods. Now, here's something interesting. The length of each period is determined by the number of electrons that occupy the sublevels being filled. Whoa, there's a lot in that sentence. Does it make much sense? Well, let's actually look at that. We know that every time we move over one element on the periodic table, we add a proton. So we find 1 proton, 2 protons, disregard that second occurrence of helium or hydrogen. You'll understand soon. 3, 4, 5. Well, that also means we add an electron to any neutral atom. Okay, so now let's look at that sentence again. The first period fills 1s, which holds 2 electrons. Well, let's write the electron configuration for hydrogen and helium. Go ahead, write it. By the time we get to helium, the end of the first period, we have filled the 1s subshell. Let's go ahead and do the electron configurations for lithium, beryllium, boron. We'll just start with those. I've written these down here, and if you look at this trend, you can probably figure out what's going to happen by the time we get to neon. That's right, neon's going to look like this. Therefore, the second period has filled all of the subshells on the second main energy level. Oh, well, that's weird. What do you think we do in the third period? If you said fill all of the subshells on the third main energy level, you'd be right. Let's go ahead and write the electron configurations for the first 4 elements going down in group 1: hydrogen, lithium, sodium, and potassium. You ready? What do you see? Well, in each case, the highest main occupied energy level is the same as the period. Oh, well, that's cool. Now go ahead and write the electron configuration for beryllium, magnesium, and calcium. What do you see? Well, again, the highest main occupied energy level, it's the same as the period. Okay, this is good. Do the same thing for boron and aluminum. Go ahead, pause the video. By golly, the highest main occupied energy level, in other words, where the valence electrons are, is the same as the period in each of these cases. Well, that in fact is what we're going for. The highest main energy level occupied is always the same as the period. So if we look back to magnesium, right there, we know it's in the third period. We don't have to count anything. We don't have to do anything. What about bromine? What would be the highest main occupied energy level for that? Ding, 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 ding. Yeah, the fourth. What about nitrogen? The second. Okay, well that's the first part of our little trick. Cool. Let's look at one more thing. Going back to these that you wrote down ever so carefully. For group 1, what else do you notice about the electron configuration for each of these elements? Well, for whatever main energy level it ends in, it always ends with an S1. So we know that lithium's in the second period. We know it's going to end on the second main energy level. But we also notice that everything in group 1 ends with an S1 configuration. Group 2. Again, that main energy level trend continues, but we notice that everything here ends with an S3. So we could write a sort of generic formula, we like those, for how each of these ends by writing N S1. Well, we know that N is main energy level, so we know this is going to end in whatever N it is, S1, N, S2. Well, let's look over here again, that boron and aluminum. How did they end? Group 13 seems to always end in a P1. Ooh. So we can look at group 13 and know immediately that they're going to end in NS2 and P1. Well, I sort of gave that away. What do you think this next group is going to end in? Anyone guessing NS2 and P2? Good guess. What about the next group? NS2 and P3, and so on, until we get over to those noble gases that are going to end with a what? NS2 and P6. Well, not helium, obviously. But everything from there on is going to end with an NS2 and P6. Wow, we have a party trick. Now, let's try using our party trick. I am going to pick phosphorus. 15 electrons. I'm not going to count anything. So, I know that it ends on what main energy level? Well, it's in the third period, so it's got whatever comes before it, and then 3, well, let's see, S1, S2, S2P1, S2P2, S2P3. So 3, S2, 3, P3. Now, if I know noble gas notation, guess what else I can do? I know that it has everything neon had plus 3s1, 3s2, 3p1, 2, 3. So I can write the noble gas notation for phosphorus without counting a thing. Holy smokes! This is the best party trick ever! Let's do rubidium. Ooh, element 37. So I know that it's in the first, well, let's get period first. 1, 2, 3, 4, 5. Okay, it's in the fifth period, so whatever. 5. And I know it's in the first group, so it's going to be 5s1 that ends its configuration. Now again, because I know that my noble gas notation would tell me that it's got everything krypton's got, plus the 5s1, I now have written the noble gas notation for rubidium's electron configuration, woo, in a snap. That's so cool. Because of these patterns, the periodic table can actually be subdivided or coded into blocks based on the sublevels that are being filled. So groups 1 and 2 are the S block, 13 through 17 are the P block, 3 through 12 are the D block, and the lanthanide and actinide series are the F block. Let's see what that looks like visually. If you'd like to color your periodic table to reflect that, you can. But here's the S block, because in those we're filling what? Well, S1, S2. Here's the P block, where we start to fill P1, P2, P3, on and on and on. Now once we get down here, we start filling Ds. And we'll actually see what that looks like a little bit more in our next video. Okay, right now what I want you to do is practice doing some trick configurations, in other words, writing the noble gas notation for something without counting a darn thing. Get going!